So the next property I'm going to prove for you is the transitivity property. So it's the transitivity of big O. Some people call this the transitive property, or say big O is transitive. And here's the way this works. And this is a common property that a lot of different mathematical objects may have. Not all of them, but some of them do. But this is how you would state it for big O. So if, suppose I give you three arbitrary complexity functions, f, g, and h, here's the statement. If f is big O of g, and g is big O of h, then you can say that f is big O of h. That's what the statement is, and this is what we're going to prove. You can see quite quickly that we have a conditional statement. So you have if this and this are true, then it has to follow that f is big O of h. One way you can look at the transitive properties, you're cutting out the middleman. So notice that I have involving f and g. So what I'm doing is I'm going to cut out the g part. So that's the intuition behind this, is that for the way transitivity works, is that I should be able to talk about f and h, and I'm going to cut out g, the middleman in here. So I'll give you an example of how you might apply this transitive property after the proof. So let's get into this proof. As per usual, I have to lay out the game plan, everybody. So here's the proof. We have to find the constants, right? We find constants. One is a positive real number. The other is the positive integer, n0. So I have c and n0, where it has to be that f of n is less than or equal to c times h of n for all n greater or equal to n0. Thought I'd write it a little differently here. So let's get in on this. So we know that f is big O of g, and we know g is big O of h, so we're just going to invoke and use existential instantiation to make that happen, okay? So we're going to come up with names for those constants. Since f is big O of g, and g is big O of h, there exists constants C1, C2, which are going to be positive real numbers. So I'm just going to pair them up based on this one involving the, so C1 is going to involve the first big O statement. C2 is going to involve the second big O statement. C1 and C2 and N1, N2 such that both f of n is less than or equal to C1 times g of n, right? That comes from the first application of the big O definition. For all n greater or equal to n1. And we also have that g of n is less than or equal to C2 times h of n for all n greater or equal to n2, right? So what I'm going to do is akin to one of my other examples. I'm just going to pick n0 right away because I would like to pick n0 such that this is true and this is true. Both of these inequalities are true. You're going to see why in a moment. Choose n0 is going to be the max of n1 and n2. Remember, this just takes the larger of the two numbers and return. It sets that to be n0. Then we find n0. Well, let's find the constant. Remember, we have to find the constant c. I haven't done it this way in quite a while. We need to find the constant c. So notice, usually we find n0 next. I'm going to find c next. I thought I'd give us an example where we're doing it a little differently. So that f of n is less than or equal to c times h of n for all n greater or equal to n0. So now we have what we need here. So now I'm going to take the two inequalities I have over here. We're going to add over both of them. Or am I? Should I do that? Probably not. Nah. In our previous examples, we would do that, but I don't want actually a statement that involves f plus g, right? We want something involving f and h, right? But here's the thing. Wait. Let's go back over here, camera. Come back. Go this way. Go this way. This way. I want to point out something that's rather important for how we're going to play this out, okay? So let's see here. Let's keep going, camera. Keep going. Okay. I think we're... Okay, there we go. So notice here. So I want you to notice, we're not going to add the inequalities, which is what we've done many, many times. We're not going to multiply them. Instead, what we're going to do is watch this. I want to say something about f and h. But notice that in the middle here, so and for this inequality, I have the c1 times g of n. Do you see how I can try to take this inequality and combine it with this one, such that this part here, it goes right here. So I want to like sandwich, I want to be able to put this in the middle between here. But to do this, I would have to take c1 and multiply it to both sides of this inequality. Then you can see it flows all the way through. Do you see that? So that's what I'm going to do, is I'm going to try to bridge the two inequalities. So using the above inequalities, which was over there, above is now left, okay, everybody? Using the previous inequalities, observe that for all n greater or equal to n0, because remember, I've picked n0 already. And we know both of those inequalities are going to be true for these values, well, for the value I picked for n0, right? So for n and, so n0 and greater, sorry, I'm getting very excited about what we're going to do here. So I know that this is c1 is less than or equal to c1 times g of n, right? And now what I'm going to do is I know g of n is less than or equal to c2 times h of n. So I'm just going to drag this c1 along, take it for the ride. Right? This is perfectly valid because c1 is a positive real constant. And next, I'm just going to put c1 and c2 together. And what's this? Well, you could pick this to be c, right? So I'm just going to select c to be equal to c1 times c2. Therefore, by the definition of big O, f is big O of h. And we're done, right? Because that's what this states. And that's how we can prove the transitive property. Now we know that big O has the transitivity property. So I thought I'll give you just one example of how you might use this. Now, in a previous session, I showed you how you can prove, say something like n to the k is big O of n to the k, right? In fact, I showed you that if you had a polynomial, like if I had a polynomial, and the way I defined it was eventually this had, the most dominant term in it was going to be an n to the k. It had like n to the k times a coefficient plus n to the k minus 1 times the coefficient and so on. We showed that this is true. In another session, I actually was the previous one to this one, I showed you that n to the k is actually big O of n to the k plus epsilon, where epsilon is a positive real constant. So if you use the transitive property, what I could conclude, and keep in mind that this exponent will be potentially a fractional or even a real number. It will be something, it might be something else. It's completely not like the polynomial rule we had earlier on in earlier sessions. What I could do is, well, this is f, that's g, this is h. So from this, I can conclude that given a polynomial, as per the way I had it in the previous session, you can conclude it's n to the power of k plus epsilon, where this is any positive real constant. So it means that you can show that any polynomial with its dominant term is n to the k. You can show that it's big O of n to the k plus epsilon. So for example, if you want it to be, like, say if you found out that this polynomial here ends up being something like n squared plus n or something like that, you can conclude that this, if for whatever epsilon you want, you can show that this is 2 plus epsilon. So if you want to make that 0.5, you can show this actually will give you the ability to say, well, at least from the techniques I've shown you, that n squared plus n is big O of n to the 2.5, for example. So this is actually one way you can generalize this property. Is that nice?